Hello students, today we will discuss the concept of moment of inertia and calculation of the moment of inertia of some common or known bodies. So before going to the moment of inertia, first we will explain that what do you mean by rigid body. So a rigid body is defined as in which the deformation is zero or so small that we can neglect the deformation. So any body which does not undergo any deformation under the action of forces, it is said to be the rigid body. So the first case figure, this is a deformed body, but in the another figure, it is not deformed at all. So that is why it is called rigid body. So there are two types of rigid body motion. One is translational or linear motion, and second is rotational motion. So first, the translational motion of a rigid body states that all the points of the body have the same displacement, the same velocity and the same acceleration at a given instant. That means suppose this is a position P and this is a position Q. So the A and A prime, B and B prime and C and C prime. So these have the same displacement, same velocity and the same acceleration. So this is called linear motion. And the next is the rotational motion. That is, a rigid body is said to be pure rotatory motion if it rotates about a fixed axis, a fixed line perpendicular to the plane of motion. So here this is the fixed axis, or here this is the fixed axis, and the fixed axis of rotation may be inside or outside of the body. That means the first case, the fixed axis is inside the body, and the second figure, the fixed axis is outside of the body. So here the mass is m1, m2 and m3, and these are the distance between the fixed axis and the mass of the body. Okay. Now, the motion of a rigid body in plane. That means suppose the rigid body is said to be moving in a plane. That means if the motion of the any particle of the rigid body is confined to a plane with some condition that for any two particles of the rigid body, their plane of motion are either completely identical or parallel. So the first case is the sphere or disk is rolling down in an inclined plane. So the motion of two particles in these rigid bodies are either completely identical or parallel. And here the second case, this is the oscillation of a pendulum in a plane. So here these are completely identical. Now we will explain the concept of moment of inertia. So this is a geometric quantity in the case of a rigid body motion. So the moment of inertia plays the same role in rotational motion as mass does in translational motion. That means in the translational motion we call the particle mass is, that is m. For rotational motion, the mass is analogous to the moment of inertia, and it depends on the axis of the rotation, mass of the body and distribution of mass about the axis of rotation. That means this y prime, this is the fixed axis, and here the masses of the rigid body, that is m1, m2 and m3, and the distance between, and the total mass is capital M, and the distance between the fixed axis with respect to m1, m2, m3, that is r1, r2, r3 and so on. So the total kinetic energy of the body is T is equal to half m1 r1 square omega square. So here the angular velocity, that is omega. So at omega velocity, it is angular velocity, the rigid body is moving with the fixed axis y prime. So the T is equal to summation I equal to 1 to n half mi ri square omega square, so where I is equal to 1 to n. So that means half omega square summation I equal to 1 to n mi ri square. So these summation I equal to 1 to n mi ri square is equal to I. That is called moment of inertia. So I is equal to m r square. Now we will define another parameters, that is called radius of gyration. So radius of a gyration of a body about an axis is that distance at which, if the whole mass of the body were concentrated, it would have the same moment of inertia as that of the body. That means the radius of gyration k equal to root over I by m. So I is the total moment of inertia and m is the whole mass of the body concentrated at a point. So that means the dimension of k, that means the radius of gyration, has the length. And for continuous mass distribution, the k is equal to, so I is equal to r square dm and m is equal to integration dm. Next, we will explain the two important theorem of moment of inertia. So there are two important theorems on moment of inertia. By these theorems, we can easily calculate the moment of inertia of the body about an axis when the moment of inertia about some other axis is known. So the first theorem, that is called perpendicular axis theorem or for a plane lamina. So the theorem states that the sum of the moment of inertia of a plane lamina, so this is a plane lamina, about two mutually perpendicular axes in its plane is equal to its moment of inertia about an axis perpendicular to the plane of the lamina and passing through the point of intersection of the first two axes. So what does it mean? That means mathematically the Iz, so there is a x, y, z, three coordinates. So Iz is equal to Ix plus Iy. So Ix, Iy and Iz represents the moment of inertia of the lamina about the Ox, Oy and Oz respectively. So in the Ox, that is a Ix moment of inertia. In the y direction there is a Iy moment of inertia, and in the z direction there is Oz direction there is a Iz moment of inertia. The Iz moment, but that means the moment of inertia at the z along the z axis is equal to Ix plus Iy. So this is the perpendicular axis theorem. Now the second theorem states that the parallel axis theorem. So what is this? So parallel axis theorem, suppose this is a fixed moment of inertia about an fixed axis. There is a AB passing through the center of mass of the lamina and AM is the total mass of the lamina and R is the distance between the AB and CD axis. So the parallel axis theorem states that the moment of inertia of a lamina about an axis, that means this axis, is the sum of the moment of inertia of the lamina about the parallel axis passing through the center of mass of the lamina. That means both axes lies in the plane of the laminae, plus the product of the mass of the lamina and the square of the distance between the two axes. That means the total moment of inertia is equal to IC plus mr square. So m is the total mass and r is the distance between the perpendicular distance between the two axes, and IC is the moment of inertia about an axis passing through this lamina. So total moment of inertia is equal to IC plus m r square. So this is called parallel axis theorem. Now we will discuss some of the calculation of the moment of inertia of some known or common bodies. So first we will discuss uniform thin rod. So suppose the rod is rotating about an axis passing through its center and perpendicular to its length. That means the suppose this is the fixed axis AB and the rod is length is L and M is the capital M is the total mass of the rod. So let us consider an element dx at a distance x. So that means at a distance x from the fixed axis, the element area, that is dx, element length, that is dx, from the axis of rotation AB. So this is the axis of rotation. AB is the axis of rotation, dx is the element length, and the distance between these axis and the dx is x, and O is the center. So the mass per unit length of the rod, that is capital M, that is the total mass of the rod, and L is the total length, and mass of the element dx, that is dm is equal to m by l into dx. So mass per unit length m by l, and the mass of the element dx, that is m by l into dx, and the moment of inertia of the element dx about AB axis, that is m by l, and this is the x square dx. So the total moment of inertia of the whole rod about AB, that is integration I is equal to integration minus L by 2 to plus L by 2. So this is 0. So the total length, that means it is a plus L by 2 to minus L by 2, m by L x square dx. That means from integrating this we can get, that is total moment of inertia is equal to m L square by 12. Now the second case is moment of inertia of uniform thin rod. So this is the uniform thin rod and about an axis passing through its center of mass and making an angle theta with the rod. That means this fixed axis is having an angle with this rod. So here the moment of inertia of the element dx about AB is di is equal to dm x sine theta whole square, because here the perpendicular distance is the x sine theta. So dm x sine theta whole square, and dm is what? M by L, that means the total mass by total length into x square sine square theta dx. Then the total moment of inertia I is equal to integration di, that means minus L by 2 again plus L by 2 m by L x square sine square theta dx. So by integrating we can say that is m L square by 12 sine square theta. So if the axis is coincides with the rod, then the theta equal to 0. That means the moment of inertia will be 0. But if the theta is equal to 90 degree, that means it is same with the previous one, that is m L square by 12. Now the third case. The third case is the moment of inertia of a circular rotating about an axis passing through its center and perpendicular to its plane. So what is this? So suppose the M, capital M be the mass and capital R is the radius of the disc. So the center is at O and the axis AB is perpendicular to the plane of the disc. So let us consider a concentric circular strip of the disc, this is the concentric circular disc of the radius x and thickness is dx. So the area of the elementary ring, that is 2 pi x dx, and the area of the plane is pi r square. Since the plane is uniform, the mass per unit area, that is m by pi r square. So the mass of the ring, that is the m by pi r square, that means this is the area of the pi r square is the area of the plane, m is the total mass, and the the area of the elementary ring, that is 2 pi x dx. So the moment of inertia of the whole ring about the AB axis, that is di, is equal to 2 mx dx by r square x square. So when we integrate over 0 to r, so here this is the radius, is total radius is 0 to r, that means we can integrate over 0 to r. So the value of total moment of inertia, that is half mr square. So if the moment of inertia of the disk about its diameter, that means it will be, so if the moment of inertia is about the diameter, then that will be I prime is equal to I by 2, that is by perpendicular axis theorem. This will be half mr square. And if the moment of inertia about the tangential component, that means by using parallel axis theorem, so the I double prime will be, so this is the mr square by 4, and this is the total IC is equal to mr square. So if we add this, so the moment of inertia about tangent, that will be 5 by 4 mr square. Now the fourth and last case is the moment of inertia of a uniform solid cylinder. So this is a uniform solid cylinder about its axis xy. So let the mass of the cylinder, suppose the mass of the cylinder is capital M here, and the radius, that is total radius, that is r, about an axis y prime. So let us consider a coaxial cylindrical shell of radius x, same as the previous one. So this is the x and the thickness is dx. Okay. So the length of the cylinder is small l and the volume of the cylinder is pi r square l. So the mass per unit length of the cylinder, that is the total mass, is m, and the volume is pi r square l, and volume of the shell is 2 pi x dx into l. So mass of the shell is, this is the mass per unit length into the volume, that is 2 pi x dl into l. So again the di is equal to this into x square, as the its radius is x, that means this is this term into the x square, and the integration will be 0 to r. Then we get again the I is equal to half mr square. Next, we will discuss the acceleration of a rigid body rolling down an inclined plane. That means this is a rigid body that is rolling down in this inclined plane. So let us consider a rigid body, that is the rigid body of mass capital M and radius of this rigid body, that is capital R, is rolling down from a plane, and the angle is the angle of the inclined plane, that is theta. So, and at the initial position A, the velocity of the body will be 0. After traversing or traveling distance x along the plane, that means this plane distance, let the velocity at the position B is, so here the position velocity is v. The vertical distance is x sine theta, and the loss of the potential energy is equal to the mgx sine theta. So if there is no loss of energy due to the friction, so here we have considered that there is no friction, so the loss of potential energy equal to the gain of the potential energy, because the total energy is conserved. The gain in kinetic energy, that is half mv square plus half I omega square, where I is the moment of inertia about the axis of rotation. So the gain of the potential energy, that is half mv square plus I omega square, is equal to the loss in the potential energy, that is called the gain in the kinetic energy is equal to the loss in potential energy. So the loss in potential energy, that is called mgx sine theta. So the omega is equal to v by r. You just put all this value, so you can get, that is v square is equal to 2gx sine theta by 1 plus I by mr square. And again, if we put that v square is equal to 2ax, then the acceleration, by simplify we can get, so this is the acceleration, where k is the radius of gyration. So acceleration is independent of the mass of the body, and acceleration is large when k square by r square is small. So for a cylinder, solid cylinder, k square is equal to r square by 2 and a is equal to 2/3 g sine theta. And for solid sphere, we know that k square is equal to 2 by 5 r square. So the acceleration will be 5 by 7 g sine theta. So acceleration of solid sphere is greater than the acceleration of solid cylinder having the same radius. So the solid sphere falls faster than the solid cylinder. So it is all about the moment of inertia. Thank you all.